Welcome back to our database design and development unit. In this lesson we will continue our design topic by looking at the design of queries. The learning intentions for today's lesson are as follows. We will learn how to analyse and extract key design information from a given scenario. We'll learn how to create a design for a query, including calculations and aggregate functions. And we'll learn how to structure the design for a query using a table. As always, we have some success criteria, and for today's lesson it is as follows. We'll be able to analyse and extract key design information from a given scenario. We'll be able to create a query design which includes fields, tables, search criteria, grouping and sorting. We'll be able to include calculations and aggregate functions in our query, and we'll be able to note the query design in table format. Planning out the design of our database operations will help to reduce the amount of trial and error that programmers have to carry out when coding. They can do this by using a simple table template. Relational database software has the capability of performing calculations and executing mathematical functions. It also has the ability to use standard arithmetic operators such as plus, minus, divide and multiply. On top of that, we can also use standard aggregate functions such as min, max, average, sum and count. When we're designing a database operation from a scenario, it's necessary to know the capabilities and apply those appropriately within our design. We will look at SQL implementation of calculations and functions later. We will now look at our first scenario. A relational database is used to store details of items for sale in a fruit and veg shop and of the shop's suppliers and linked tables. The profit that an item makes is calculated by subtracting the price the item is bought for from the price that the item sells for. The shop would like to know the largest profit for fruits and vegetables. The largest profit should be listed first. The first step in this is to extract the key information from the scenario. For example, we're looking for the profit. That is calculated by subtracting the price the item is bought for the price that the item sells for. We're also looking for the largest profit for fruits and vegetables, and the largest profit should be listed first. The first step will be to examine the sample data to see that data in context. This will allow us to identify the entity and attribute names. We'll also carefully check expected output to scaffold the design of the query. Just to be clear, joins do not need to be included within the query design. The scenario talks about fruit and vegetables which can be found within the field type. The expected output also includes the field type. Profit is not an existing field in the database. This is a calculated field using the existing fields buying price and selling price. The result of that calculation has been given the alias profit. We'll cover aliases later. The profit must also only contain the maximum calculated value. This is identified using the max function. In the tables row, we clearly identify where we get that information from. In this case, all the information we are using is contained within the item table. For search criteria, there is no search criteria in this case, therefore that is left blank. In the grouping row, again we will cover grouping later, we will group these by type. We'll talk about grouping later, but the reason we group it by type is because we want a single value return from our aggregate function against each type. And finally, we will sort this information. The sort order will be the highest maximum profit for each type from highest to lowest. That's why it's descending. Let's now look at scenario 2 and extract the key information from that scenario. Firstly, we'll read over the scenario. A car dealership uses a relational database to store information about their cars, customers and salespeople. A customer would like to buy a car from the years 2017 or 2018. They want to know the cheapest asking price of the 2017 and the 2018 cars that are currently on sale. We'll extract the key information, such as we want to look for a car from the years 2017 and 2018, and we want the cheapest asking price of 2017-2018 cars which are currently on sale. Again, we'll examine the sample data to see the data in context and to identify the entity and attribute names. We will also check the expected output carefully to scaffold the design of our query. And again, just a reminder that joins do not need to be included within the query design. From the information we extracted, the scenario talks about the year of the car. The expected output also includes the field name year. We also talk about the cheapest price, and that is not an existing field in the database. This value is calculated using the min function applied to the asking price field. The result from that function has been given the alias cheapest price. Again, we'll talk about aliases later. The tables or entities we extract this information from are clearly indicated. In this case, it's car sale. We have some criteria in this case. The years have been defined as either being 2017 or 2018, and we can see that with year equals 2017 or year equals 2018. We also have another part of the criteria which says cars which are available for sale. In this case, the sold field will have to be no. Again, we are using an aggregate function, and for that case we will have a grouping because the aggregate function will always return a value. We want to have that value against something. In this case, we are going to group this separately, and we are going to group that against year. And finally, we are going to sort this information by year ascending. So therefore we have the output of this query showing the cheapest price of a car that is available for sale in 2017, followed by the cheapest price of a car which is available for sale in 2018. Thank you for listening. Please like this lesson and subscribe for more content.